Okay, everybody, this is 5-4 day 1. So today we're going to look at basically non-linear transformations. What happens if your data is not linear? So usually this is an activity. So everybody's given a bag of M&Ms, similar to what this is. There's 60 of them. So you pour them out, count the number of M&Ms, and record the amount in trial 0. So we have 60. I make sure every pair has a group. I can't talk. Every pair of people you work with a buddy has 60 M&Ms. Then what we're going to do is we would shake them up, and then pour them out, and then remove any where the M's are M side up. So I would remove like however many. I usually let the students eat them, or you can just kind of put them on a different paper. Basically until either 8 trials have happened or you run out of M&Ms. Now, because I don't want to waste your time with you like seeing me, do all this, I'm just going to give you the data from earlier when I did it. So I started off with 60 M&Ms. After I shook everything up, poured them out, and got rid of the ones that were M side up, I had 30 M&Ms. So then I shook those 30 up, poured them out, removed any M side up, then I had 16. I did it again and I got 7 left. I did it again and I got 4 left. I did it again, I only removed 1. I shook those 3 up, didn't remove any of them. Shook those 3 up again, didn't remove any of them. Shook those 3 up, and then I got to remove 1. So this is the data we're going to work with, just so that we can save time so you don't have to watch me with the M&Ms. Because that's not really the important part. The important part is the next steps. So what I'm going to do in list 1 and in list 2, I'm going to plot the data. So this one's kind of important to follow along because we're going to be doing some residual stuff. So I'm going to go to Stat, Edit, put my trials in. So there's my data. It's very important, remember, if you are doing this on your own, do not put 0 in for Y, because eventually we're going to have to take the log. So plot the amount of M&Ms remaining Y against the trial X and describe the pattern. So we're going to do a scatter plot of list 1 versus list 2. I'm going to hit zoom 9. So what should end up happening is you should end up getting sort of an exponential decay scatter plot. Okay? So as the number of trials increases, the number of M&Ms remaining decreases. Okay, so here's my pattern. Now, when we do this in class, everybody has a little bit of a different pattern, but overall it's exponential decay. So check to see if Y is being multiplied by 0.5 each year by calculating the common ratio. A common ratio is greater than 1 is an indicator of exponential growth. If it's less than 1, it's exponential decay. So if I went through and I divided like 30 divided by 60, I would get 0.5. 16 divided by 30, 0.53. Really, this should be down 1. Sorry. 4 divided by 7. So if you look, it's kind of close to 0.5 until we get to the very end, right? And then we have 1, 1, and then 0.66. So it's not the same every time, but it definitely is getting smaller, except for these two. Now in list 3, what I'm going to do is I'm going to take the log of each number in Y. So when I go to my list 3, hoping you can see this. I'm going to go up like that, so that list 3 is highlighted. I'm going to hit log, and then I'm going to hit second number 2. So log of list 2. So what we do in this class, instead of like changing our line, we're going to change the data. So I'm going to make all the y's, I'm going to take the log. So there's my new list. Now I'm going to plot list 1, list 3. So I'm going to go to my scatter plot. Now I'm going to plot list 1, list 3. So I took the logs of the y. So I'm going to change those values. Now I'm going to plot that. Sort of looks a little bit more of a line. It's still sort of curved a little bit, but there is a stronger linear relationship. It's still negative, but now it's a little bit more linear than it was previously. So what we're going to do, calculate our least squares regression line, find r and r squared with list 1, list 3. Describe the strength of the relationship and record your least square regression line below. So I'm going to go to Stat, Calc, go to number 8, but now I'm doing list 1, list 3. So we transformed our data because it wasn't linear, but now since we transformed it and it looks linear, we can do our linear regression. So notice I have log of y hat 1.564 minus 0.1788x. And I didn't turn my stat diagnostics on. I forgot. So let me turn that on. Do this again. R here is negative 0.943. Again, that's where that strong negative. And R squared is 0.8884. Okay, so that's where you have that strong negative, now linear relationship. Just make a note, notice our equation now says log y hat. So before we were just using y hat, now we have the log, because we took the log of the y values. Construct and interpret a residual plot for log y hat on your trial numbers. If your equation from step 5 is in y1, all you need to do is enter list 4, the residual. So I'm going to go back to Stat, Calc, nope, Stat, Edit, excuse me. Go up to list 4. Now hit second stat. Since we already find our least squares regression line, this resid shows up. That's your residuals. And then you can just hit enter. So there's all my residuals. You just have to be careful. You cannot do this until you've done step 5, in that you need to find your linear regression line first, and then you can find your residuals. So now I'm going to sketch list 1, list 4. So the x values versus our residuals. Sorry, I'm going kind of fast, but oops. So there's my residual plot. So I'm just going to draw a sketch. Describe the pattern. Does it appear that the values are randomly scattered above and below the line y equals 0? No. Here there is a curved pattern in the residual plot. Therefore, our transformed data is not, actually this should be our transformed model, is not appropriate. So we need to transform the linear equation in step 5 back to the original units. So this will require an inverse transformation. Since we took the logs of each y in step 4, we simply need to undo the step by taking the equation that was in y1 and taking it to the exponent of 10. So all I'm going to do in my y equals, I'm going to do 10 to the power of my equation up here. And now I'm going to plot this line with my original data, with list 1, list 2. So there's my line. I'm going to go back to the scatter plot. Because now we're saying it's not appropriate. So let's really look at the graph. Oops. It's going to be a second because now it's going to hit the wrong button. Zoom 9. So there was my data. Now see how the line doesn't really fit, especially over here. So it doesn't really fit, which is why it's not appropriate. So it's a better fit than a straight line. But it still doesn't fit all the data. And that the reason is because this is like an experiment, right? Not an experiment, an observation, no, an experiment. We have like data, so we have user error. So it's not going to be a perfect 100% fit because this isn't a perfect exponential decay graph. If this was like a perfect exponential decay, the line probably would fit better. So using your new exponential model equation in y2, what is the predicted number of M&Ms for trial 3? So we're going to do log y hat equals 1.564 minus 0.1788 times 3. So we're going to find the predicted number of M&Ms I should have had. So log y hat equals 1.0276. To get rid of the log, remember log is base 10, I'm going to exponentiate. So I'm going to take both sides to the power of 10. So y hat is 10 to the 1.0276 power. So I should have 10.66 M&Ms in trial 3, when in actuality I had 7. So again, not a perfect fit. So the point is for you guys to realize, and we'll talk about this on 5.4 day 2, in this class, if we have something that has an exponential relationship or what looks like an exponential relationship, we log our values, either we log y, x, or both, so that our curve, we can do linear regression and it fits the data. So your homework is to do this, the spread of AIDS data. So you're going to put this in your calculator and kind of do something very, very similar to what I just did. And then that's it, really. So normally we do this in class, and obviously the counting of the M&Ms and everything takes a long time. But because I'm just recording, we could do it a little bit faster.